All right, so we're now moving into the calculus portion in the calculus textbook this semester. So this material is going to come from section 2.1 from the calculus textbook, and that can be accessed through our Canvas page. The very first page should have a link to the calculus textbook. So why don't you pause, copy this out, and then I'm going to throw some additional stuff on there. All right. We are going back to a topic we first covered when we were doing lines a couple of weeks ago, linear functions. And that is this notion of an average rate of change of a function. So the average rate of change of a function f from x equals a to x equals b is given by, well, it's the change in the outputs over the change in the inputs. So we would calculate f of b minus f of a all over b minus a. All right. Graphically, I want to get a graphical sense of what we've just done. This fraction, f of b minus f of a over b minus a, that is a slope calculation. So we have taken 2 points on the graph of f, a comma f of a, b comma f of b, and we have calculated the slope of a line connecting those 2 points, okay? A line that goes through 2 spots in a function is called a secant line. Secant line. All right. So this means the average rate of change of f from x to a is the slope of the secant line connecting a comma f of a and b comma f of b. Right? So we have this sort of algebraic view of how to calculate an average rate of change, and we have a graphical interpretation as to what that average rate of change is. It's a slope of a line we call a secant line. All right. So again, we're going to do an example now, calculating some average rates of change. So pause, copy this down, and then I'm going to fill in some work here. Okay. All right. So we have a function, s of t is equal to 2t squared plus 3. And this function is measuring the distance in feet that an object has traveled t seconds after it starts. So the output, the distance is measured in feet, the input is measured in seconds. And I'm going to find some average rates of change between different times. And please note, I'm always going to start at time 1. Okay. So the first one I'll do slowly, and then I'll just tell you some numbers for the second one. All right. So the first one, I'm going to calculate the distance traveled at time 3 minus the distance traveled by time 1 all over 3 minus 1. Okay. Now, when I plug 3 into my function, I have 3 squared is 9, times 2 is 18, plus 3 is 21. So you should check, but I get 21 feet for s of 3. And then if I calculate s of 1, I get 1 squared is 1, times 2, that's 2, plus 3 is 5 feet. And 3 minus 1 is 2, and that was being measured, time was being measured in seconds. So I think I get 16 over 2 feet seconds, which is the same as 8 feet per second. So the average rate of change between time 1 and time 3 is 8 feet per second. So over this 2-second long period of time, on average, I was traveling 8 feet per second. The object was traveling 8 feet per second. All right, so now let me do the next one. It's going to be identical. I'm just plugging different numbers in. So I'm going to get s of 2 minus s of 1 all over 2 minus 1. And here's where I'm just going to not tell you how I got these numbers. The 2 and the 1, I just plugged them back in. And let's see, I got 11 minus 5 over 1 So I got 6 feet per second. So my average rate of change from 1 second to 2 seconds was 6 feet per second. So on average, during this 1 second period, I was going 6 feet per second. All right, now please note this average rate of change of position, the units are feet per second. So that's like velocities. So the next three, I'm just going to say instead of average rate of change, I'm going to say average velocity, since the rate of change is the velocity for this particular problem, okay? All right, so I'm going to do the average velocity from time 1 to time 1.5. So last time I'll write it this way. I'm going to do 1.5 plugged in minus 1 plugged in all over 1.5 minus 1. And when I crank that out, I get 7.5 minus 5 all over 0.5. So I get 5 feet per second. And you can check on the calculator. I get 2.5 divided by 1/2, and that's 5. So as I keep my clock closer to time 1 second, it looks like my average velocity is coming down a little bit. All right, now I'm going to go from time 1 to time 1.1. So what's my average velocity over this 1/10 of a second? And if I crank the numbers in, I get 5.42 minus 5 all over 1.1 minus 1, okay? And that gives me 4.2 feet per second. And if I go from time 1 to time 1.01, so 1/100th of a second later, I get 5.0408. That's S of 1.01 minus 5. That was S of 1 all over 1.01 minus 1. And when I crank that into my calculator, I get 4.02 feet per second. So if you look at these numbers, as that second time value gets closer and closer to time 1, these numbers are changing, going from 8 to 6 to 5 to 4.2 to 4.02. And one of our goals is going to be seeing, well, where do we think those numbers are converging to? Is there like some value down here they're getting really close to? All right. Okay, well, keep this in mind. I'm going to put some of this information onto my next slide graphically to see what's going on. All right, so what were we doing in that last problem? Well, I had the point at 1 comma S of 1 on my graph of position, my S of t function, okay? So the first one I did was the average rate of change between 1 and S of 1 and 3 and S of 3, right? And as I said in that very first slide, this is telling me the slope of the secant line, okay? So that slope was 8. The average rate of change was 8 feet per second. So that slope was 8, okay? The next one I did was from time 1 to time 2. So there's my dot at time 2. And my average rate of change was the slope of that secant line, which I believe we had 6 feet per second. Then I did time 1 to time 1.5. So there's time 1.5. And it's getting hard to see now, but I've got a secant line in between those. And that guy had a slope of, we said, 5. And then I got even closer. From 1 to 1.1, I made a secant line, and I calculated the slope, and I got 4.2. And then even closer, and I got a slope of 4.0202, okay? All right, now what's fascinating here is if I reproduce my graph just to clean it up, hopefully. I had these secant lines, and I had some more of them. But what's interesting is I can introduce this idea of a tangent line that just glances the graph of f at time 1. So this is tangent line. to my function, sorry, my function's name is S, at time 1. So we had a secant line that touches the graph in 2 spots. The tangent line touches the graph in 1 spot and just sort of glances off of it, just touching it at that 1 point at time 1. And what's interesting is the slopes of these secant lines are starting to get closer and closer to equaling the slope of this tangent line. Okay. All right. And I call the slope of that tangent line the instantaneous rate of change. So the average rate of changes were the slopes of the secant lines. And my goal in the next few weeks is going to be to try and figure out the instantaneous rate of change of my function. And that's going to be the slope of this tangent line. All right, sorry, I got way too close to you there. So summary, pause, copy, play. So in summary, the average rate of change of a function from x equals a to x equals b is the slope of the secant line between the 2 points. And that slope, m sec, let's call it, is f of b minus f of a all over b minus a. It's rise over run between 2 points, right? Then the instantaneous rate of change of f at x equals a is the slope of the tangent line to the graph of f at x equals a. And the idea we're going to be getting at is as my b value, as that second point gets closer and closer to the a value, my secant line slope gets closer and closer to my tangent line slope. In other words, my average rate of change gets closer and closer to my instantaneous rate of change. And we're going to spend a few days developing this idea. But average rates of change are slopes of secant lines. Instantaneous rates of change are slopes of tangent lines. And as our secant line points get closer and closer together, sorry, as my secant line 2 points get closer and closer together, the secant line starts to look more and more like my tangent line.